All right, thanks, Tim. I'm Stanford Gibson. I'm a sediment transport specialist at HEC. Let's just start out with 2D sediment transport and RAS. Here's the story of how it happened. Basically, there are two ancestral lineages of 2D sediment transport and RAS. One is, many of you know that we have subgrid bathymetry in blue water RAS. And so that came from Vincenzo Casuli's scholarship, and it kind of worked its way through the RAS team, who made it actionable with all the cool things you like about RAS. And that's how the 2D model happened. Meanwhile, over in Vicksburg, Alex Sanchez was writing a model called CMS that's based on, his advisor was Wei-Ming Wu. And so that came to be. And then Alex Sanchez started working at HEC about the time we were starting to do 2D sediment transport, and got posed with the challenge of how are you going to do 2D sediment transport with a subgrid model, and made it happen. And that is 2D sediment transport in HEC-RAS, and it is awesome. But it's kind of a big ask. If you've got project funding, if you've got confidence in your both 2D hydraulic modeling skills and your sediment transport intuition, this is the thing to do. But what if you don't have skill or budget? Can you just not do a sediment transport analysis if 2D hydraulics are on the line? And so I've been thinking a little bit about legacy and career, and what I actually want to do with my time in the Corps. Now that it seems like I am in fact a lifer and I'm not going anywhere, what's it going to look like? What do I want to do? And I figure I basically have two mission statements. One is I just want to provide the state-of-the-art sediment science as it leverages the usability and familiarity of RAS. People use RAS. People are familiar with RAS. RAS has great interfaces. Let's get the best sediment science we can into that. And that's what Alex Sanchez has really done, is really taken state-of-the-art sediment science and put it in the state-of-the-art hydraulics in RAS. And that's great, but I also have kind of a competing objective. And my competing objective is to avoid sediment failure modes in the course projects and the projects of everyone who uses RAS, which means that we're going to avoid more sediment failure modes if people are doing more sediment analysis. And so these are competing objectives, because the better and more detailed we make the sediment model, kind of the fewer people will feel qualified to use it. And so I essentially have two visions for sediment and RAS. I want to make it better, but I also want to make it easier. And so that's what we're going to talk about today. We're going to talk, I could give a very impressive talk about 2D sediment transport, and I've given that talk and it's online. I want to talk about the second bullet, about what if you don't have budget? What if you don't have confidence, but you sniff the potential of a sediment failure mode? Can you just not do anything, or is there stuff you can do? And we have added a new suite of tools in 2D that lets you do 2D screening level analysis. And so this is my conceptual model of really any engineering analysis, but particularly morphological analysis, is that you essentially have two axes. Basically, what do you do as an engineer? What do you do as a morphological scientist? Why is that a job that actually gets paid, although my friends don't actually believe it is? And that's, what are we selling? We're selling increments of risk reduction. And so generally, the more risk that you reduce, the more it costs. And so you can kind of work down this staircase or this waterfall of different approaches to reduce morphological risk, from engineering judgment to expert elicitation to geomorphic assessment, down to 1D, 2D, 3D modeling. A lot of times you'll just want to get into physical modeling, and ERDIC is just, the well-known stuff down at ERDIC has just revolutionized physical modeling. It's available to us in ways that it never used to be, at budgets and time scales that it never used to be. It's fantastic. And then eventually, maybe a prototype experiment is actually what you need to do to reduce risk, if risk is high and uncertainty is high. But you'll notice that there's kind of a split here. And that's the split between the qualitative approaches to uncertainty and risk reduction and the quantitative approaches. And there's this zone in the middle where you might want to be quantitative, but you don't have a lot of time or budget. And this is where Ron Copeland, many years ago, came in and helped with his team down at URDIC develop the SAM program. The SAM program was the sediment analysis module. The idea is that it's an expedited sediment analysis tool. It lets you do a lot of sediment analyses without having a full-blown model. And so it's in this like low effort quantitative space. And so many years ago, we added the hydraulic design editor to HEC-RAS. And the hydraulic design editor does a lot of the things that SAM did and some other things. And the idea is that these hydraulic design tools, which you can get to, if you've never pressed this button in HEC-RAS, you're missing out, because there are some fantastic things, including we've added a riprap calculator and a tool that actually downloads sediment data from the USGS and does statistical analysis with you. I won't say for you. And so this is a sweet spot. And so let me tell you a story of how we used this and then how we ran out of the ability to use this and had to add something for 2D that sets up the things that we did in 2D. And that story surrounds the Iao sediment study in Maui. So this is the Iao Basin, and I did this with Nani and Jessica at POH. It was an RSM study. And let me just kind of pitch the problem to you. This is a alluvial fan downstream of the mountain that is Maui, right? And so it's the volcano, and so they get tropical rain on the volcano, and just these huge sediment slushes come off, almost debris flows. And so in order to protect the town, there are two things that protect the town. One is the debris basin upstream so that the channel doesn't get choked with sediment. And then the Corps has a flood risk management project downstream since like the 80s with this kind of alluvial channel and levees. But what ends up happening is all the sediment gets caught, all the big sediment gets caught in the debris basin, which the Department of Transportation of Maui has to spend maintaining this single debris basin. Meanwhile, all that sediment's that getting caught up there isn't transporting downstream, and so in the core flood risk management channel, we're getting erosion and widening, and in some places eroded more than 7 feet. And so this was an RSM study. We wanted to do something quick. We wanted to get an idea of, can we change this detention basin to let more sediment through and deposit in essentially two birds with one stone, the basic RSM model of we get less deposition upstream, more deposition downstream without inducing downstream deposition problems. It wasn't a huge amount of funding. We just wanted to do something quick and get some analysis. And so we entered the hydraulic design function. And the hydraulic design tool that we used was what we call the sediment transport capacity calculator. We just have a 1D model, and we're going to compute sediment transport capacity. And the idea is we're going to look at how capacity changes in one dimension downstream and see if the channel has enough capacity to move more sediment if we let more sediment out of the debris basin. And so Jake Helminiak actually did some of this work, and the idea is that, okay, we're going to send sediment through the debris basin, and then, we've got pretty good capacity through here to move any sediment we want to put through the debris basin. We're not going to induce any deposition that's going to cause flooding until we get about to the bridge down here, and then capacity drops off a cliff. Problem is that if we deposit down here, this is a community, and it's more expensive and more controversial to remove sediment from this part of this region. And so, the mandate is if we are going to manage sediment, we can't induce deposition here. And so if you look at the capacity computed by multiple transport functions, you'll see the trend you're used to seeing with multiple transport functions, order of magnitude of difference, but telling the same story, which is why orders of magnitude of difference don't cause me to lose sleep like they used to. And so what you'll notice, this is the bridge, and in every case, sediment transport capacity pegs down at the bridge, suggesting that, sure, you might be able to pass sediment through most of this system, but it's going to deposit at the bridge, which is the worst possible place it could deposit. And if you go out there, you see deposits at the bridge. Here's the problem. I didn't believe it. I thought that was wrong. And here's why. Because I built a 2D model, a hydraulic model. I didn't have time to build a 2D sediment model, but I built a 2D hydraulic model, and the velocities through this area were high. And so I thought, why would it deposit at the bridge? Yes, I have 1D evidence, and I have physical observations, but I still don't believe it because the 2D model says that the hydrodynamics, this should actually be a high capacity zone. So what I did is I went and I wrote an R script. If you don't know, HEC-RAS output is an HDF5. And so HDF5 output is nice because you can write R, Python, or MATLAB code against it if you're that kind of person. And most engineers are one of those kinds of people. And so if you look at in the RAS users manual or the online documentation experience, as I like to call it now, I actually have some sample code in each of these that show you how to interact with the HDF5 output. And so I just wrote a little R script that basically harvested the transport capacity. I tricked my model into thinking it was a sediment transport model without actually depositing sediment. And then I went and I harvested the transport capacity at each of these nodes and added them up and looked at how the transport capacity changed with flow. And the 2D model said, hey, you have more than enough capacity here. You're going to move 8,000 tons, which is more than the 10-year event delivers to the basin. And so this is not depositional hotspot according to the model. So now I have conflicting evidence, and conflicting evidence is an invitation to curiosity. And so curiosity began. But what you'll notice now is that the zone in which I had funding to answer this question is gone, because now this is a multidimensional question. But the HD calculators and the 1D modeling, which is kind of what I do, are no longer available to us. And we didn't really have time or funding to scale up to a 2D model. So what are we going to do? It's cute that I created a trick model and then wrote R code against it to come up with this result. But that's not a workflow that I can offer the public. And yes, we do projects for the Corps of Engineers, but we're primarily model developers. And if I told you that the workflow was to write R code, that would be me not doing my job. So Alex Sanchez and Alex Kennedy and Anton Rosiran, they added some new outputs so that you could just look at capacity in a mobile bed model. Still a mobile bed model, but you could look at capacity. And so here I'm plotting capacity in the concentration color scheme. So blue is high capacity and brown is low capacity. And so you can see that the model is saying we have plenty of capacity through here. We do have a capacity shadow on the right bank. And so if we were going to deposit, I would expect it to be on the right bank. But you go out there and you look, there's no deposition on the right bank. All of the deposition is in the middle and the left bank. And so now I'm thinking the 2D model is just wrong, that I should trust the combination of 1D and experience. But there's another line of evidence that we just don't take into account enough, and that's local experts. And so there is a team of guys out there that move this sediment around. And so I just talked to them and I said, listen, my model says that we should be depositing in the right bank. And when I look at this, it's all in the middle and the left. And they're like, oh yeah, it always deposits in the right bank. We just got in there with our bulldozers and moved it over to stage it. And so now I have a model that works, that actually fits the behavior. And so this is what it looked like after an event in 2019. And you can see that a lot of the deposition is in the right channel. We do have some left channel deposition. We'll get to that. And so now I have a conceptual model. We have this flow shadow on the right. That's where the deposition starts. Okay, we're good to go. Then in January 2021, there was a 10-year event. And I was going there in March. I was like, I can't wait to see what happened in the bridge. I can't wait to see the deposition that happened at the bridge after a 10-year event. And here's the deposition that happened at the bridge after a 10-year event. None. The 2D model was more correct than the 1D model in my first look at the physical evidence. And here's what's going on. Basically, the depositional hotspot is in the pier shadow. And the shadow of the piers is creating a flow shadow where you get the founder effect. You get your first bar. Once that first bar forms, you are down the road to alternating bars in the downstream channel. And so I kind of built this little conceptual model. You generate this one downstream bar. It grows and vegetates. The flow field moves around it, and then you're on to alternating bars. These alternating bars form until they choke the downstream channel. And what happens is they choke the downstream channel until the whole thing fills with sediment, and the sediment actually progrades upstream through the bridge. But the bridge itself is not the hot spot. So we worked our way to an explanation of what the depositional failure mode at this project is and how to do that. And we did that with a simplified 2D capacity result. And that was really cool. And it provided us with a lot of insight with not a lot of work. And I thought this tool has to be just generally available to people. And so in version 6.4, what Alex Sanchez and I did is we added what we call these fixed bed sediment transport modes in RAS, so that this is not much, this is about half an hour more work than a hydraulic model, and it's not more computationally expensive. What you do is you just go in and you define a bed gradation, so you do need to use the sediment tools, but only to set the bed gradation. None of the other parameters really matter. And then you choose this capacity only mode and you can do this analysis. So fresh out of 6.4 being released, I got a call from Edmund Howe, who's on the call and who's on the presentation. His whole team's here. And Edmund, the story he told is that they had been asked to analyze a 2004 feasibility study in about 6 months in order to determine if the plan to dump 3.1 million tons of rock in 11 pools along 336 miles of the Arkansas River was appropriate, or if they could do a better analysis in 6 months on 336 miles of river. Now, if you know Edmund, you know that the answer was yes, we can do better. So Edmund called me up and we went to Little Rock District and we taught the 2D sediment transport class. And with all the equations and all the mobile bed stuff, and the class was super engaged because they knew they'd have to use it immediately. And but in the back of my head, I was thinking 6 months is not enough time to do 11 pools and 336 miles to produce real answers on 1,900 proposed structure modifications. That's just not reality. And so these features were brand new. And so we actually did a talk and workshop on the capacity only features. And what Edmund and the team did is they took those 11 pools and they found 11 modelers. It's almost like a multi-core computer at that point. They spun off these analyses to multiple modelers. Many of them went to Katie Martin, who I need to mention. She took this on early and did a lot of these models early. You'll see her name there a lot. But that was the plan. And they applied the capacity only approach. And here, the idea was, could we combine a capacity only analysis, which is something we could pull off in 6 months on this scale, with some sort of design heuristic? And so this is the Little Biometro bend, which they like to call patient zero. And the idea here is this was one of the most problematic bends. They had to dredge this bend 22 times since the 70s. And then they went in, they put in these structures, and they didn't have to dredge again. It fixed the problem. And so the question is, could we use this to develop a heuristic? So the idea is, if we run this in capacity only, what kind of capacity change moves the worst case scenario to no problem? And that will bound the signature that we need to see in the other structures. And so we ran capacity only with and without the structures. Here I used the RAS mods in order to take the structures out. Usually when we go from without project to project condition, we're adding something, but here it's already there, so we actually have to take it away. I have a little YouTube tutorial on how to do that if you're interested. So here's the capacity maps at the same color scale with and without the structures, and it's exactly what you would expect. The sediment transport capacity gets pushed inside, but these runs took seconds. They took seconds compared to a sediment transport model, which could take hours. And a lot of the sediment transport modeling complexity is with the bed change. And so let me just demo this, because slides are slides. And I actually have RAS open on my machine, so let me show you. So here are the structures, and I used the mods to create a terrain without the structures. And so then we have the capacity map without the structures and the capacity map with the structures. So then you can use the raster calculator, which if you haven't used, you're going to love it. And I do have a video on that as well. And so you can difference those, and you can see the difference in the capacity. You can go into the profile lines, and you can plot the capacity with and without. I have to turn on the results again to do that. You can plot the capacity with and without. And you can see what has changed, how those structures have just changed the transport capacity. Well, now that we've done that, there's our heuristic. We basically doubled capacity. Those structures basically doubled the capacity. So that's your end member in your analysis. By doubling capacity, you made the worst case scenario not a problem. And so in the 50 to 70% capacity reduction, for most cases, it's probably going to be a good case. And the districts and the team kind of dialed in that assumption, but then they went in and they used the channel mod tools to do a bunch of channel mods and look at how the structures change capacity. And here's pool 2, which I worked on, and this just scales. Right now, what we can do is we put in the 2004 recommended modifications, and you can see the capacity hotspots and the kind of corresponding depositional zones. And so here's one, and incidentally, ERDIC went out and got ADCB data, which is just beautiful if you're doing 2D modeling, especially if you're relying on the hydraulics and your sediment transport isn't going to kind of tell on you. And so we calibrated in several places to the depth cross-section and the velocity cross-section. And then we're analyzing this structure right here. The structure is not out there now. That's part of the proposal. And you can see that through here, essentially we're doubling capacity. We're reducing capacity through here, but it's about a 5% change, so that's probably not going to induce a depositional problem. And then down here, we're increasing capacity by a factor of 3, so maybe that's over-engineered. And so what happened? So the team has analyzed 4 of the 11 pools, and they've already reduced the rock by 500,000 tons of rock. That's, they're up to $38 million of savings, and they did this in less than 9 months. Now, most of that goes to, this is a really high quality team doing really hard, working really hard and really smart to get to an answer. But I like to think our contribution here at HEC is we provided some tools that help them get there, and that could help you get there if you find yourself in a situation where you don't have the money, you don't have the supervisory buy-in, or you don't have the timeline to do a full morphodynamic model. You can still analyze morphological failure modes. And so we're kind of back to where we were, where we have this gaping hole between qualitative and quantitative analysis. You go straight from geomorphic assessment and sediment budget to a 2D model. Well, now you have some tools that are intermediate complexity that can help you think about that. Now, you'll notice that it's capacity only, which I've talked about twice, and concentration only. Let me tell you a little bit about how you might use concentration only. Concentration only is a little bit more robust. Now you're going to actually define your sediment boundary conditions, but you're not going to change the bed. We're just going to use the advection diffusion approach, the solution that Alex coded, to route the sediment through with some sediment sinks and sources, but a lot of the computational expense and a lot of the headaches, honestly, come from bed change. And so we're not going to change the bed. It's still going to be fixed bed, but we're going to let you route sediment through your system. If, for example, you want to do a TMDL analysis or something like that, but bed change doesn't matter. But the place where this is going to provide the most power is in mud and debris flow modeling. Now, if you haven't heard me talk about mud and debris flow modeling, I've done that a lot, so I'm not going to go too deep into this now. There's some videos online. But the basic idea is we've added non-Newtonian mud and debris flow modeling to RAS. And that's great. We're getting great results. The biggest limitation of mud and debris flow modeling in RAS is that you're required to input a single concentration in all time and all space. Now, if you've got this massive rapid debris flow, that's not a terrible assumption, but there are some cases where that breaks down. And so basically you had two options. You could use a constant concentration in all time and space, or we don't advertise this, but there's nothing that keeps you from adding non-Newtonian physics to your unsteady flow model and running a full 2D sediment transport analysis. So if you want to vary concentration in time and space, you could run a non-Newtonian 2D mobile bed sediment transport model. And the number of people who have done that are Alex Sanchez. I haven't even done that yet. That is a big lift to answer a problem that generally people want an answer to in days. If there's been a fire and there's a storm system coming in, people want to know about their mud and debris risk in hours or days. And so we need an intermediate option. And that's where this concentration-only analysis comes in. And so I think the best case for this is Eagle Creek, which flows into the Columbia River just upstream of Bonneville. They had a massive wildfire there. And so the question is, after this wildfire, if a mud and debris flow came down off of Eagle Creek, would it impact Bonneville Dam? And so you can imagine that a mud and debris flow, you can imagine how a single concentration for this whole system doesn't work, right? Because you've got a mud and debris flow coming from the tributary into blue water, and you want to see how that's going to mix and move downstream and if it's going to affect the dam. And so now, with the concentration-only approach, you can build a simplified sediment transport model, a fixed bed sediment transport model that just moves the sediment down essentially the concrete channel. It doesn't actually work like that yet. Well, I'll tell you about it. But essentially, that's the way I would think about it. You want to move the sediment down this concrete channel, give it the opportunity to deposit as the shear stress decreases, but then eventually, when it hits this water, to disperse and just use the advection diffusion equation to see what happens to it. And so this is actually an animation. It's a GIF actually, or a GIF, depending on who you are. I am agnostic about that. And you can see that now we can bring the sediment pulse into the Columbia River and see how it affects and if it reaches, which it doesn't, Bonneville Dam. So by providing these fixed bed sediment transport models, we allow these like lower fidelity but still powerful sediment transport analyses on some of these rapid evaluation problems. And incidentally, we are adding a tool to 6.5 that's going to make this better. We're adding a threshold deposition so that now you can just send the sediment down and it will stay in suspension until it reaches a depositional threshold like in the Columbia River and starts to deposit. Okay, so far I've framed this problem in, let's say that you want to do a lower fidelity analysis. You don't have time or budget to do a full 2D sediment transport model, but you do want to be responsible about morphological failure modes because you are in the river engineering working group and you know that is probably the primary failure mode in core projects. But I named this talk an incremental approach to modeling complexity. And that's because even if you are funded and do have time to do a full 2D morphological model, you still should take an approach that considers incremental complexity. And so one of the most fun things I did this year was at SedHide. I invited several sediment model developers. Me and Alex were there, and then we invited Gary Brown, who developed SedLib that's used in ADH, and then Blair Greiman, who was involved in the SRH suite that the Bureau of Reclamation uses, for a panel discussion, which we recorded and are going to run on the podcast, about sediment modeling failure modes and best practices. And one of the things that we hit was that again and again and again, we have to tell people to take an incremental complexity approach to modeling. The most common problem I see with sediment transport models is we have all these great data. We have really detailed bathymetry. We have everything we need to build a super complex model, and so we do. We put our terrain in, we make the mesh really detailed, we add all the structures, we add all the data, we press compute, and if it runs, it doesn't calibrate, and then we don't actually know where the model was because we added all the complexity at once. We didn't add increments of complexity and then evaluate them to see if they made sense before we moved on to the next one. But the incremental complexity approach lets you evaluate where your model failed as you add each increment. And so the incremental complexity model to model formation is actually in our guidance. This comes straight out of the Thomas Copeland tradition. If you were to look at documentation that Tony Thomas and Ron Copeland developed for how to build a sediment transport model, it is an incremental complexity approach. They say first you do your hydraulic calibration. You fix the flow, you fix the bed, and then you vary the flow and you fix the bed. Then you do what Ron calls a robustness test, which is a steady flow mobile bed analysis. You fix the flow and you allow the bed to move to look for structural errors or structural instabilities. Then you do your dynamic calibration with a variable flow and a variable bed. Notice they're just assuming you're doing a dynamic calibration in a sediment transport model. They're just saying there's at least 2 steps that come before that. Well, now what we've added is the ability to do an intermediate step, a 1.5, where you're going to do fixed bed sediment transport analysis, where your flow can either be static or variable. The Arkansas team did both. And your bed elevation is fixed, but you can look at capacity and evaluate how your model changes the capacity in your system. I just have to tell you that I have found that since we started working with Arkansas, I've been on calls with at least 5 or 6 districts where I've told them either, yeah, you don't have budget for a 2D model, but you should definitely do a capacity-only analysis, or do a capacity-only analysis to determine how you should set up your model or even collect your data. That's the end of my story. But let me just say that I mentioned that this panel discussion is going to be on season 3 of the podcast. If you don't know that we have a river mechanics podcast, this is really honestly the most fun thing I've done in a long time. So I'm going to pitch it. We have a river mechanics podcast, the RSM River Mechanics Podcast. I'll put the link in the chat, but you could just look for it on Apple or Spotify or Google. And we just finished releasing season 2, which is a reservoir-centric mini season. We just talked to the best people. Like I'm not going to be modest about it. We talked to the best people. We talked to George Annandale. We talked to Greg Morris. We talked to Paul Boyd and John Shelley and Jennifer Bountry. This was really fun. And then season 3 is almost all recorded. And in season 3 we did some things that are a little bit different. We still talk to core legends. We talked to Tony Thomas. We're going to talk to Jim Selgin. But we also talked to more professors this time. We branched out. The podcast is kind of caught on outside the core. And so I thought, well, let's also talk to people outside the core. We talked to David Montgomery, Marcelo Garcia. Just last week, I talked to Peter Wilcock. So season 3 is going to start to come out in like November, December. But we've got 2 seasons up there if you're interested. All right. And so that's my story. I'm happy to take any questions.